Hello, friends. Welcome to the online lecture series of digital communication. I am Assistant Professor Mr. V.R. Wadekar from Department of Electronics and Telecommunication from Matoshi College of Engineering and Research Center, Nasik, affiliated to Savitribai Phule, Pune University. We are studying spread spectrum modulation. So let's start with our today's video. In today's module, guys, we are going to study about direct sequence spread spectrum. But before that, let's have a quick revision. In our previous lecture, we have studied about a spread spectrum technique. That what is spread spectrum, why we need it, what are the applications of it. Then we have discussed about PN sequence, that is pseudo noise generator, why it is required, how we are going to generate it, and what are the properties of it. So today, let's study about direct sequence spread spectrum. Now, each bit in original signal is represented by multiple bits in the transmitted signal. And the spreading code, it spreads signals across a wider frequency band. And this spread, it is in direct proportion to number of bits that we used. And the one technique, it combines a digital information stream with the spreading code bit stream. It is using what? XOR gate. Well, this is the direct sequence spread spectrum BPSK model. The spread spectrum technique that we discussed in a previous lecture, it is called a direct sequence spread spectrum. And this technique, it can be used in a practice for a transmission of a signal over a bandpass channel, such as your satellite channel, then BPSK it can be used. So you can see on the screen that this is the data signal. It has been given to this binary PSK modulator, and to this PSK modulator we have used a carrier over there, and the output of this modulator, it is S of t, it is a modulated wave. And after this, now we are going to spread the bandwidth of the signal. So we have used a PN generator over here, and this is nothing but your XOR operation that takes place at this instant, at this place. So C of t, it is nothing but your PN sequence code. S of t, it is a modulated wave. And the output of this is nothing but your X of t, which is a spreaded signal. And then it has been given to the receiver over this channel. Then after this one, at the receiver side, this signal is received as Y of t. Over here, again, this is a local PN code generator, which is in synchronized with that generator at the transmitter. So output of this modulo 2 adder, it is U of t, which has been given to this coherent detector, which has been given by this local carrier. So the despreading operation, it has been taken place at output of this modulo 2 adder, and the output of this coherent detector, it is nothing but your estimation of your data signal that we transmitted. So if a threshold is set for logic 1 and logic 0, and if the incoming bit it is above threshold, it is declared as logic 1. Otherwise, it is declared as logic 0. So as per the diagram, as you know, x of t is nothing but your s of t into c of t. What is x of t? It is nothing but your spreading signal. S of t, it is your BPSK output signal. And what is C of t? It is a PN coded data signal. And now the channel output, it is given, if you have observed, J of t. So Y of t is equal to what? X of t plus J of t. What is J of t? It is an interference signal. And as we already know that X of t is equal to what? C of t into S of t. At the receiver, the channel output Y of t is initially multiplied by the PN code C of t. So U of t is equal to what? It is C of t into Y of t. But Y of t, it is nothing but your C of t into S of t plus J of t. So if you are going to expand this bracket, you would get C square of t, S of t plus C of t into J of t. But as we know that C square of t is equal to 1 as per PN code properties. So we can write it U of t is equal to S of t plus C of t into J of t. So this equation, it shows that the input of coherent detector U of t, it comprises of S of t added with the code modulated interference signal C of t into J of t. Now this is the Dirac sequence spread spectrum BPSK waveform. As you can observe it over here, this is the user data. And this is your PN sequence, that is C of t. And when we are going to do the XORing modulo 2 addition of these two signals, you would get the spreaded signal, that is S of t. And this is since a BPSK output, so you can see it that when the phase it is going to, when the shifting it is going to take place from 1 to 0 or 0 to 1, the phase shift it has been occurred. This is nothing but your transmitted BPSK output. And at the receiver, this is your detected despreading code. So it is a 1 1 and it is a 0 0 1 and so on. And this is the PN sequence code which is exactly same as that of your transmitter, which is in synchronized with this one. And after this one, we are going to do the XORing operation of Y of t and the C of t, and you would get the estimated value or the detected B of t. See, this is the sent one, transmitted, and this is the received one. So hope so you understood the operation of Dirac sequence spread spectrum, its mathematical analysis and its waveform. And this is the spectrum of your DSS signal. This is the spectrum of your data signal. This is the spectrum of your pseudo noise signal, and this is your spectrum of your combined signal. Well, now, what are the advantages of Dirac sequence spread spectrum? It provides a good discrimination against multipath signals that we already discussed in previous module. Performance of DSS system in the presence of noise is much better as compared to FSS system, frequency of spread spectrum, that we are going to see in the next module. And it reduces the narrowband interference like jamming signals effectively. Next, the disadvantages of DSS. It is a system, it has a long acquisition time. It requires a wide band channel and high PN code data rates are needed. Now look at this waveform. On the basis of it, now we are going to see the processing gain, probability of error, jamming margin. So you can observe it over here. This is your data signal, which has a bit period of a TB. And this is your PN, there's a code signal, which has each bit, it has a period of TC. And you will find the period of this PN code and the spreaded signal, it is same, that is of TC. So by using this waveform, now we are going to find the processing gain. So let's start with it. Processing gain is defined as the ratio of a bandwidth of spread message signal to the bandwidth of unspread data signal. That is bandwidth of spreaded signal upon bandwidth of unspreaded signal. It is nothing but your process gain. Now for the NRZ bipolar signals, you know the bandwidth of the signal is equal to 1 upon 1 bit period. So 1 bit period, it is what we have seen, it is a TB. So the waveform of the data signal, spreading signal, and the spreaded signal MT are given as we have seen in the previous figure. So we can write it, the bandwidth of the data signal, it is nothing but your 1 upon 1 bit period, which is nothing but your 1 upon TB. So make it as equation number this. Now the spreading pseudo noise signal C of T is multiplied by the data signal, and the spreaded message signal M of T is produced. And this waveform M of T that we have seen in this previous figure. And if you have already observed, I told that 1 bit period in message signal M of T, it is same as that in what? Spreading pseudo noise signal C of T, which is nothing but your TC. So the bandwidth of spreaded message signal, we can write it as 1 upon TC, that is the 1 bit period. Now putting the values of this bandwidth obtained in this above in equation 6.5.3, we obtain the processing gain is equal to what? It is equal to 1 upon TC upon 1 upon TB, or we can write it TB upon TC. So this is nothing but your processing gain, which represents the gain achieved by processing the spread spectrum signal over an unspreaded signal. And as we already knew that 1 bit period TB of a data signal is equal to what? N bits period of spreading pseudo noise signal, that is TB is equal to NTC. Since putting this value of TB in above equation, you would get processing gain is equal to what? N. Now, talking about the probability error of DSS BPSK system. As we know, the probability error of coherent BPSK that we already seen in previous modules, that is probability of error is equal to 1 by 2 error function square root of EB upon N0. N0 by 2, it is nothing but the noise spectral density, and EB, it is nothing but your bit energy. So for direct sequence spread spectrum modulation, the noise spectral density unit is given by N0 by 2 is equal to J into TC upon 2. Make it as equation number this. So 2 get cancelled. So N not NO is equal to what? JTC. Which is J, it is nothing but your average interference power which has been given to this channel. Therefore, this equation, that is 6.5.9, it would become what? EB upon JTC. Half of error function EB upon JTC, make it as equation number 6.5.12. Now, talking about a jamming margin. Well, we know that EB, it is the bit energy and it is equal to PS into TB, where PS is nothing but your average signal power and TB, it is nothing but a 1 bit period of the data signal. So considering the ratio of the signal energy per bit to the noise spectral density, that is EB upon N0 is nothing but your what? PS into TB upon N0, because EB is equal to PS into TB. Now putting the value of N0 that we found in 6.5.11, that N0 is equal to JTC. So we are writing PS into TB upon JTC. So separating this term, this is the new equation. So we can write it J upon PS is equal to JB into TC, JB upon TC into 1 upon EB by N naught. And as we know that TB upon TC is nothing but your what? PG, that is processing gain. Therefore, the above equation, write it J upon PS is equal to what? PG upon what remain? EB by N0. This is next equation. Hence, then the ratio, J upon PS is nothing but your jamming margin. And it is a ratio of average power of interference, that is the J, and the data signal PS. So in the form of a decibel, we can write it PG of dB minus EB upon N naught dB. So in decibel jamming margin, it has been given by this equation, processing gain dB minus 10 log of EB by N naught to the base 10. So students, today we have discussed about the direct sequence spread spectrum with coherent BPSK, its transmitter, its receiver. Then we have done the mathematical analysis of it. We have seen the waveform for it. And then we have seen about the processing gain, probability of error, and the jamming margin. So it is the next assignment that you need to solve it. In next module, we are going to study about a frequency hop spread spectrum. So thank you very much, students, for being with us.